Okay, folks, welcome to our June 5th meeting of the Ottawa Centre, Royal Astronomical Society of Canada. A special welcome to other RASC centres that might be joining us here this evening. So before we proceed, I'll go to the next slide. Oh, there we go. So just practicing good security here when we're on Zoom. We do not monitor the chat box during the meeting, but somebody, nefarious person, may try to come in and put in links and things like that in the chat box during the meeting. So please do not click on any links that are posted in the chat box. If you have a question for any of the speakers, please use the Q&A box at the bottom. And what will happen is that I'll be monitoring that. And as a question comes up and it's appropriate and at an appropriate time, I will read the question out so that it does get captured in our recording. And then we can hear the response from the panelist. Next slide. Okay, so here's tonight's program. We're going through the introduction right now. I've got a 10-minute astronomy news. I've got the Ottawa Skies for June. Jim Thompson's going to be talking about his filters, part 3. And we have so many observations that the second section is going to be just observations. Right after the break, we're going to have our standard M&M challenge over the break. It'll be a 5-minute break. And we got some amazing pictures that have been submitted for this month. So without further ado, let's move on to the next one. Okay, so welcome new members. We've got 6 new members there. So we've got Abu Sis, Jeff Burney, Ernesto Luke, Bernja Chaldrick, Michael Sauchgau, and Jonathan Falbo. And I'm sorry if I mispronounced your name there. We have members in the news. So congratulations to Robert Dick, whose article on general scotobiology about light pollution. And please check out his article in the June edition of the RASC Journal. And to remind you that this coming Sunday, we're having the virtual General Assembly. And we've got special guest speakers starting at 11 o'clock on Sunday, right through until 2. And then the actual annual general meeting takes place at 6 p.m. And I believe you need to pre-register for that. And you also need to know your RASC membership number in order to attend that meeting.
Dave, if I can intervene for a second, it's Chris.
Sure.
And just remind people that the times you just listed and the times on this screen are in Pacific time because the GA is in Vancouver.
Okay, so good point.
I want to add 3 hours to these, and I'm quite sure I have already added 3 hours when I put the note there about 6 p.m. for the AGM.
Okay. All that information is available on the rasc.ca website as well. Okay, next one. Okay, 10-minute astronomy news. So first slide, please, Chris. So this article is from ABC, the Australian Broadcasting Corporation, an article that I found. I thought it was quite interesting. And I've got a bit of an interest in radio astronomy, so this is sort of right up my alley. So after an intergalactic search lasting more than 2 decades, an Australian-led team of scientists say they've finally found the universe's missing matter, solving a mystery that has long stumped astronomers. Since the mid-90s, scientists have been trying to locate half of the universe's ordinary matter. They believed it was out there because of clues left over from the Big Bang, but it had never been seen. What we're talking about here is what scientists call baryonic matter, which is the normal stuff that you and I are made of, said Associate Professor Jean-Pierre Macaut from the Curtin University node of the International Center for Radio Astronomy Research. Astronomy is full of missing stuff. Most of the universe is understood to be dark matter and dark energy, which nobody has ever directly seen. But even more of a mystery for astronomers was that they couldn't find out about half of the ordinary matter in the universe. It's been a true embarrassment that we haven't been able to find it, said Professor Xavier Prochaska, an astronomer from the University of California in Santa Cruz. Astronomers have been looking at the universe using all sorts of different forms of light, from radio waves to X-rays and visible light. None of them revealed the missing matter. That was until they started to measure fast radio bursts, brief flashes of intense energy found racing across the universe, and discovered the missing matter hiding in the cold dispersed gas between galaxies. Intergalactic space is very sparse. Missing matter was equivalent to only 1 or 2 atoms in the room of the size of an average office, Dr. McCart said. Fast radio bursts, FRBs, were first detected in 2007, but are not fully understood. As FRBs travel across the universe, they are dispersed and slowed down by the matter they pass through. Each frequency of radio energy is slowed down differently by that matter. I'll get the next slide, please. So just like a prism spreads light into a rainbow of colors, each with a different frequency, the missing matter in the universe spreads the FRBs out into different frequencies. By studying how far away the origin of the bursts were and how much they have spread out by the time they reached the Earth, the scientists were able to figure out how much matter was sitting between the galaxies. Repeating the process with 6 different FRBs coming from different parts of the universe, the team was able to figure out how and where the missing matter was. The results were published on May the 27th in the scientific journal Nature. You can go back to the previous one there, Chris, and run the video. Hopefully, there it goes. Okay. It was a great feeling to have that measurement and to know something that you think only a small number of people in the world know, to put it to bed a cosmic mystery, Dr. McCart said. So this is showing how the matter, as it encounters it, does modify the frequencies. There we go. Okay, so next slide. Seeing such tiny changes in the FRBs required a mammoth effort using a combination of massive radio and optical telescopes. The team used the CSIRO Australian Square Kilometre Array Pathfinder, an array of 36 radio telescopes in Midwest of Western Australia. Combined, the dishes equate to a single radio telescope with a 4,000 square meter dish. That's a good sized radio telescope. Next slide, please. They have the ability to look at a huge area of the sky in high resolution. That means without knowing where an FRB would come from, they were able to capture it and analyze exactly how spread out each wavelength in it was. Then the aptly named Very Large Telescope in Chile measured the distance between the Earth and the galaxy that the FRB came from. With those 2 pieces of information, the researchers were able to determine how much matter was in the otherwise empty space that the FRB passed through. Next slide, please. The discovery still leaves much of the universe undetected. About 85% of its matter is thought to be dark matter, that which is undetectable using ordinary methods. I like a mysterious universe. It means there's much more to be understood, Dr. McCart told the Australian Broadcasting Corporation. I think it's really exciting, said Professor Tara Murphy, an astronomer from the University of Sydney who was not involved in the research. It's the first step to using fast radio bursts to probe the invisible universe, she said. Dr. McCart said the next step was to get an intricate understanding of this newly found matter using 100 or more FRBs. The thing that we've discovered is the atmosphere of the universe, he said. It's the ecosystem in which the galaxies live. He said by understanding its precise structure, astronomers would be able to better understand how galaxies were born and what happened to them when they died. It will be like a medical image of the universe, he said. Thank you. Okay, so let's take a look at the Ottawa skies for June. So here are our moon phases, and as would happen tonight is a full moon, which we will not be able to see because we have a thunderstorm rolling through Ottawa right now. And we have the new moon on the 21st. We have Comet Swan. And where this little orange arrow is on the left-hand side here is approximately tonight. It's pretty low in the sky. I believe it's a morning object, very low on the horizon, and I think we might even have some images of this particular comet. So that's the path that it's taking right now. Well, we're moving towards the longest day of the year, and as you can see, the sun rise and sets, so the length of the days is certainly getting longer. And June 20th, 21st, we're going to the longest day of the year. Then things will improve for us. The skies get darker earlier. Next slide. Mercury. I did send an email out to the group. The greatest eastern elongation was yesterday. I'm not sure whether we're able to see it in Ottawa. It looks like there were a fair amount of clouds up there. Probably you'll still be able to see it for the next day or two. It's just after sunset. Look for it in the western sky. Venus is visible in the early evening and then the early morning. It's setting earlier and earlier. By the end of the month, you'll have to watch for it in the morning. Mars is visible currently before sunrise. Jupiter is visible late evening and through the night. By the end of the month, quarter to 10, Jupiter will be rising. So probably by about 10:15, 10:30, you'll be able to see Jupiter in the evening skies towards the end of the month. Saturn is visible late evening and through the night. So right now it's rising at midnight. And by the end of the month, it'll be rising at 10 o'clock. Uranus is visible before sunrise throughout the month, as is Neptune. And here is our cartoon of the month. Okay, we'll move on then. Okay, give me a second here.
Okay, Dave, it's Chris. I'm going to stop sharing so that Jim can take over sharing.
Okay, not a problem.
All right, everybody can see that screen, all right?
Yep.
Great. Okay, well, welcome everyone to part 3 of my presentation series on understanding astronomical filters. Tonight, I will discuss what I call special filters, those that do not strictly fit into the 2 categories I discussed in the first 2 presentations, namely color filters and light pollution filters. Specifically tonight, I will discuss the following special filter types: UVIR blocking, neutral density, those for planetary observing and imaging, chromatic aberration correction filters, something called a neodymium filter, and finally solar filters, breaking that up into both white light and extremely narrow band. So in general, these filters all draw upon the same technologies as the other filters I've discussed. They use a combination of absorption and reflection to achieve their desired spectral response. They are designed to fulfill very specific tasks, which can sometimes mean they won't see a lot of use in your toolbox, depending on your observing habits. Because of their specific applications, there are also not very many vendors for these types of filters, and as a result, they can be rather expensive. The first special type of filter to discuss tonight is the UVIR blocking filter. This filter type is intended for imaging only, since the human eye is not sensitive to these wavelengths of light. UVIR blocking filters are used to pass only the visible spectrum, resulting in sharper and better focused images. This is so because most lenses and telescopes are designed to properly focus only the visible spectrum, not ultraviolet and infrared as well. Included in this group are so-called color correction filters. And you can see the spectral response for a couple of examples in the plot on the right. The blue and the purple curves are examples. Their purpose is to modify the spectral response of a camera sensor to make it more like the human eye. All commercially available digital cameras today have some sort of color correction filter installed. Unlike the other special filters I will discuss tonight, UVIR filters are very common and are readily available from many different retailers. A word of warning, however, that many of the filters available today have a poor response to hydrogen alpha. Take, for example, the color correction type 1 shown in the blue curve. If you look at the response down around 656 nanometers, you can see that it's a pretty poor response. It's down around 10 or 15%. And that is pretty typical of commercially available camera color correction filters. So if you're looking to buy a UVIR blocking filter for your kit, pay attention to what the filter's spectral response is to make sure that it has good hydrogen alpha response. Of the many different brands that I've encountered, the one sold by Bader Planetarium is one of the better performers. And that is the green curve on the graph there. That's an example from Bader. The next type of special filter to discuss is the neutral density filter. This is a purely absorption type filter whose purpose is to attenuate the brightness of the object you are observing uniformly across all wavelengths. They are available in a variety of optical densities, or OD, meaning you can usually find the right filter for your application. The percent luminous transmissivity, or percent LT, of a neutral density filter can be calculated from the optical density using the equation shown here. So for example, if the filter has a optical density of 0.6, that works out to a transmissivity of about 25%. Another option for reducing brightness is something called a variable polarizing filter. This filter is in fact two linear polarizing filters stacked on top of each other. As you rotate one filter relative to the other, you change how dark the filter is. Many observers prefer the flexibility of a variable polarizing filter over having a selection of neutral density filters with various optical densities. The next category of filter to consider are those meant for planetary observing. Historically, astronomers have used color filters in an attempt to darken planet surface features and make them more visible. By applying interference coding technology to this problem, unique filters that accentuate multiple surface features simultaneously can be created, something a simple absorption type filter could never do. There are a number of planetary contrast enhancement filters available commercially, most of which are designed specifically for improving the view of Mars. In my experience, these filters work, some better than others. But just like when you're using color filters, the improvement is very subjective. Of the filters I've tried, none really stand out as being all around better than a simple color filter. I also have a general caution regarding the transmissivity of these filters. Many of these filters cut a very large percentage of the incoming light, making them unsuitable for smaller aperture telescopes. For example, the Orion Mars filter, shown with the purple line on the graph to the right, I've personally found too dark to use even with my 8-inch Schmidt-Cassegrain. For those who are interested in imaging the moon or the planets, there is another type of special filter that may be of interest. These filters take advantage of the fact that cameras have a wider spectral response than our eyes. This opens up an opportunity to image the planets using wavelengths of light we can't normally see. Infrared pass filters are very popular because of their ability to steady seeing conditions to provide much sharper images. You can see an example on the upper left, the moon imaged at various wavelengths, with the infrared image being the sharpest. They can also be used to view features that are not visible in other wavelengths of light. I especially like to use an IR pass filter when imaging the moon, especially when imaging from inside the city where the seeing is normally quite bad. UV bandpass filters are also popular for those interested in imaging structure in the clouds of Venus, or for imaging different distributions of elements in the clouds of the gas and ice giants. There are few vendors of UV bandpass filters, so they do tend to be a little expensive. The next category of special filters is that meant for the correction of chromatic aberration. Different wavelengths of light bend or refract by different amounts in the glass medium, such as a lens. When designing a glass lens for a telescope or a camera, this fact results in all the colors of light not coming to a focus at the same point, leaving the resulting image blurred by a violet, blue, or sometimes red fringe. Centuries of lens design has struggled to correct this problem, culminating in the multi-element exotic glass apochromatic refractor. Apo refractors, however, are still expensive to manufacture, putting these high-performance telescopes out of the reach of many amateur astronomers. The more affordable runner-up in performance is the achromatic refractor, which, although better than a simple spherical lens, still has some chromatic aberration. When viewing bright objects like the moon or planets, this aberration is often visible enough to hamper your viewing. As you can see in the image in the bottom left, the difference between an apochromatic view and an achromat view. The violet fringe is quite visible in the achromat view. The solution most commonly used is to add a filter that removes the unfocused violet-blue end of the spectrum. These filters commonly go by the name of fringe killer or minus violet. You will find that these filters are more effective when used during imaging, since camera detectors are more sensitive at the UV end of the spectrum than our eye. There is benefit to be gained, however, using these filters visually. I have personally used the beta fringe killer, which is the red curve on the plot there to the right. I've used it on my 80mm refractor, and I can confirm that the filter does what its name suggests. If you are looking for a cheaper solution to chromatic aberration, try using a yellow Raton number 8 filter, shown by the yellow curve on the plot. It should help. Using a color correction filter, you should be prepared for the fact that your view will have a yellow color cast. Depending on your specific telescope, the increase in sharpness and contrast may be worth the false color. A category of special filter that I have already briefly mentioned in my other two presentations is the neodymium filter. The concept of using neodymium, a rare earth element, to infuse the glass in an astronomical filter is somewhat serendipitous. The resulting glass media has multiple pass bands in the visible spectrum, and by some strange happenstance, the end result is a surprising increase in perceived contrast. These filters are available from a number of manufacturers, and they provide good contrast improvement with high overall transmittance. I personally use the Beta brand Moon and Sky Glow filter, shown by the red curve on the plot, whenever I view or image the planets or the moon in color. There are a number of variations on the basic neodymium infused glass filter that tailor the filter for different applications. Some have interference coatings added to provide UVIR blocking, making them good for imaging. The Beta filter is an example of that. Some have additional blocking in the violet blue end of the spectrum to improve the performance of achromatic refractors. The purple and the yellow curves on the plot are examples of that, also made by Beta. All in all, They are a curious family of filters that are worth having a closer look at. Note, however, that even though some manufacturers say that these filters provide light pollution reduction, the amount by which they do so is negligible. The last special filter category that I will discuss in this presentation are those meant for solar observing and imaging. Astronomers have been looking for ways to safely observe the sun longer than they've been looking at the stars and planets. As a result, there are a number of different options available for use today. The main problem is that the sun emits a large amount of energy, not just in the visible spectrum, but in the UV and IR bands as well. In fact, only 45% of the solar radiation reaching our eyes is in the visible band. The simplest and probably the oldest method of viewing the sun is with a pinhole camera. By putting a small hole in a piece of cardboard, you can project an image of the sun onto a screen and safely view it. This works surprisingly well. A good science project for your kids. However, it can be hard to see the projected image in the broad daylight. This concept can be taken a step further by using a normal refracting telescope with an eyepiece to focus even more light onto a projection screen. The resulting image is brighter and has more contrast. However, it will end up heating up your telescope and eyepiece. It is not recommended for larger aperture refractors and not at all on reflectors. It was John Herschel, the only son of famous astronomer William Herschel, who first proposed the idea of using a wedge-shaped piece of unsilvered glass to split off a small portion of the incoming sunlight from his telescope for safe viewing. The sunspot sketches in the figure on the lower right are in fact sketches made by John Herschel using one of these devices. The wedge prism splits off less than 5% of the incoming sunlight, dumping the other 95% out the back of the prism. The reflected 5% is then passed through a neutral density filter to reduce the light intensity to a safe level. This system, now called the Herschel wedge, was further improved by Ignazio Porro in the late 1800s by placing the glass wedge at an angle to polarize the reflected light, thus allowing a rotatable line polarizing filter to be added to give adjustability to the brightness. Herschel wedges are still available today, and many users are convinced that they give the best light views of the sun, and I wholeheartedly agree with that. I have one myself. The main drawback of Herschel wedges is that all of the sunlight gets focused inside of your telescope, causing potential heating problems. They are therefore only suitable for smaller aperture refractors, below 4 inches, and definitely not suitable for any type of a reflector, be it a Newtonian or a Schmidt-Cassegrain. Another drawback is that Herschel wedges tend to be rather expensive, in the $500 to $800 range. Luckily, filter coating technology has come to the rescue of reflector and large refractor owners. Depending on how much money you are willing to invest, you can choose to go the way of white light observing, which can be rather affordable, or narrowband observing, which tends to be rather expensive. Both systems use an energy rejection filter, or an ERF, to remove 99% or more of the incoming sunlight. In white light systems, the ERF takes the form of a mylar film or a glass filter with multiple layers of a metallic compound coated on it. The ERF is easily mounted over the sun-facing end of your telescope and can be full aperture, or spanning the full diameter of your objective, or it can be off-axis, spanning only a smaller diameter circle to one side. Off-axis ERFs are usually recommended for large aperture reflecting telescopes, anything bigger than 6 inches. as it removes the loss of contrast due to the reflector's central obstruction. And the effective increase in focal ratio helps reduce the appearance of atmospheric distortions. A big advantage of front-mounted ERFs is that they eliminate any risk of overheating inside your telescope. White light ERFs are affordably priced and can be purchased from manufacturers like Bader Planetarium, 1000 Oaks Optical, or Orion Telescopes. The white light filter also gives you the ability to add a bandpass filter to your setup, allowing for study of the sun using different wavelengths of light. Extremely narrowband solar observing systems are use specially designed ERFs that are precisely matched to the narrowband pass filter. The most common type of narrowband system used for the sun is hydrogen alpha, but there are other pass bands used as well, such as calcium K or sodium. Calling the H-alpha filter narrowband is an understatement. A narrowband hydrogen alpha filter for deep sky imaging has a pass band around 3 to 7 nanometers wide, while for solar observing they are more like 0.02 to 0.09 nanometers wide. Now, up to this point, I've been calling these devices filters, but strictly speaking, they are not filters. They are something called Ethelons. Both function using the same principle of the interference of light, but implement the idea differently. As in an interference filter, light enters an Ethelon, passing from air into the optical media, often glass, and partly reflects, partly refracts at the boundary between air and glass. Some Ethelons use an airspace between two semi-reflective coatings instead of a clear glass media. By carefully selecting the distance between the semi-reflective layers and their reflectivity, the Ethelon can be made to selectively pass a particular wavelength of light. The passed wavelength can be further adjusted by either varying the distance between the layers or rotating the Ethelon relative to the incoming light. This is an important characteristic of Ethelons, as it allows the observer to tune the Ethelon to account for wavelength variations in the hydrogen alpha emissions coming from the sun. You maybe haven't thought about it, but the relative speed difference from one side of the sun to the other due to its rotation is enormous, on the order of 14,000 kilometers an hour. This speed difference, plus that caused by the Earth's rotation and its orbital velocity, all result in the wavelength shifting up or down away from the nominal hydrogen alpha emission line. This is a characteristic that was first predicted by Christian Doppler in 1842. As one can imagine, the precisely applied reflective coatings and the ability to finely adjust the spacing or orientation of the Ethelon makes these devices very expensive. ERF plus Ethelon packages for small aperture telescopes range in price from $800 to several thousand. The cost of buying these packages separately has made solar scopes, such as those from Lunt or Coronado, with the ERF and Ethelon fully integrated into the scope, another possible alternative worth considering. There is no doubt that these narrowband systems provide by far the best views of the sun. Whether or not the view justifies the cost is a decision you will have to make for yourself. So my final words, this concludes the three-part series on astronomical filters. I'll be happy to ask any questions that you might have. You can find copies of the presentations and a lot of other material on filters at my website. The address is shown here. And you can feel free to contact me by email after the meeting if you have a question about filters. Thank you very much. And
I've got one question here.
Sure. Sure.
So first question, varying the air pressure and the air gap will also tune the Ethelon, is that correct?
I am not positive how the pressure tuned works. If the pressure changes the distance between the Ethelon surfaces, or if it's changing the angle, that I don't know.
Okay.
I do know the expensive systems sold by Daystar in the US, they actually vary the temperature of the Ethelon, and by increasing its temperature, they can make the material expand and vary the distance very finely.
Okay.
But the pressure tuned, I'm not sure.
Okay. Are there any other questions? No, I think that's it. So thank you very much, Jim.
You're welcome.
Okay, folks, we're going to take a 5-minute bio break, but we do have a Messier and Moon challenge for you to ponder while we are taking that break. So Chris, if we can go to the next slide. Okay, so there's your Messier object and there's your Moon object. See if you can figure out what they are, and the answer will be in 5 minutes. 1 minute to go. There we go. Okay, let's move on to our next slide. Our 5-minute break is over. See how well you did. Okay, so our Messier challenge is the Eagle Nebula, and I believe we might even see that again tonight. And the moon was Poseidonus, the crater Poseidonus, and hopefully you got one or both of those. So we're going to move into our observations. Just for the folks who are the panelists here, actually go to the next slide. Just take a quick look and see what order you're in. I will call you out as it's time for you to come up. And I'll also spotlight your video so that people can see your face while you're talking about these things. And folks, if you have questions about the videos, or about the pictures, observations, please type them in the question and answer box, and I'd be happy to pass those on to the speakers. So first up, we have Jim Thompson.
All right. Thank you, Dave. So May was a very busy month for me for astronomy. It started out with Astronomy Day on the 2nd, which was a great success. And we also had many lovely clear evenings in May. I got out 6 evenings in total during the month, 4 of which were all-night sessions going from 9:30 to 3:30 in the morning. Being springtime, I focused mainly on observing galaxies. I have a selection here captured from my various sessions through the month, some of my favorites. All of these were taken from my backyard in central Ottawa. So the first group of galaxies are all face-on spirals. I like the fact that there's a lot of variety in the shape and structure of these galaxies. You never know what you're going to find as you're exploring through all of these galaxies. We have examples of classic spirals like M51, which happens to be one of the observing challenges this month, or M99, which I hadn't observed before, actually, before the night that I caught that image. They all have clearly defined arms with dust lanes and star-forming regions, making them very interesting to study. Some more unusual galaxies like M66 or M96 have a more distorted structure or oddly shaped spiral arms. I also happened to catch 2 of the supernovae that are visible right now, one in M61 and one in NGC 4567/68, which is a pair of interacting galaxies called the twins. All of these were captured using my 10-inch Ritchie-Chrétien with a focal reducer to give a focal ratio of about 6. I captured the images using my Malincam Skyreader DS432 monochrome and an Optolong Night Sky H-alpha filter, which is essentially an infrared high-pass filter that I chose to use in order to cut through all of the light pollution in my backyard. These are all 20 to 25 frame stacks at 25-second exposures apiece using 6% gain on the camera. Next image, please. So this is a collection of edge-on spiral galaxies that I observed in May. Again, there's a big variety in the shape and the structure of the galaxies that are out there to observe. Some have very prominent central bulges, like M104, the Sombrero Galaxy, or NGC 4565, which is known as the Needle. Others are very long and thin with no discernible bulge at all, such as NGC 4217 or 4302, which is the edge-on one in the picture, the middle right, where there's two galaxies shown. In some cases, the details in the dust lanes are also visible, like in M108, the Surfboard, NGC 3628, the Hamburger, or 4627, the Whale Galaxy. I observed several dozen galaxies over the course of a few nights, but there are many, many hundreds more to explore. So I can't see getting tired of studying galaxies anytime soon. Next image, please. So this is one of the observing challenges for the month. I believe it's the difficult one. This is Leo 1, a dwarf galaxy. You can just make out the scattering of stars in the middle of the frame. This is a small satellite galaxy that orbits the Milky Way. It's about 820,000 light years away and is thought to be one of our galaxy's most distant satellites. It has about 20 billion solar mass, which puts it at just over 1% the mass of our galaxy. And it's a difficult observing challenge because it is so diffuse and spread out. Plus, it's very close to the bright star Regulus in Leo. And you can actually see the glow at the bottom of the frame and the diffraction spikes from that star just off the edge of the screen to the bottom. Next picture, please. So this is an area of the sky called the Coma B galaxy cluster. It's a really fascinating area with many, many galaxies visible. The cluster is thought to have at least 1,000 identified galaxies in it. It's located about 321 million light years away, and it's one of two main parts in the much bigger Coma supercluster. In this image that you see, most of the points of light are in fact galaxies. And if we go to the next picture, you'll see I've annotated the image with a circle around each galaxy to just let you know how many are in there. So the red circles are all the galaxies that are in the NGC or IC catalogs. The blue are galaxies that are in the PGC catalog, but only down to about magnitude 19. So I count in this one picture 173 galaxies, not including anything in there that's dimmer than 19 magnitude. So pretty cool when you think about it. Next image, please. So this is my image of Hickson 50. Canadian astronomer Paul Hickson published the catalog of compact galaxy groups in 1982, the catalog that bears his name. It contains 100 compact galaxy groups identified by Hickson from photographic plates. Astronomers are interested in compact galaxy groups because they readily show the effect of dark matter, since the visible matter is not enough to hold these groups together based on their speeds. Hickson also noted that most of the groups contained active galaxies, galaxies in the process of interacting with each other, and ample amounts of intergalactic gas and dust, making them also very interesting targets for study. Amateurs use these objects as observing challenges, with number 50 being the most challenging, as it is by far the dimmest in the catalog. I was able to achieve 11 of the Hickson galaxy groups in one evening. I believe it was on the 22nd of May, with number 50 being my favorite. It's located in the sky very close to M97, the Owl Nebula in Ursa Major, but it is very far away, about 1.7 billion light years. The 5 members that you see here in the enlargement range in magnitude from 18.4 to 19.7, which is quite dim, and why it is considered one of the most challenging Hickson objects to observe. Now, I also happened to catch a number of even dimmer galaxies in this image. And a friend of mine, Denis Legault, helped me to identify one of them, PGC 66200088, which is also shown in its own enlargement. And it, if you can believe it, has a magnitude of 22.2. So not too shabby from my light polluted backyard, I have to say. Moving on to the next image, please. So this is my last deep sky image to share this month. It's a bit of a tease, as it is traditionally a summertime object. You have to stay up pretty late, or early as the case may be, to see this object. It's not high enough in the sky to observe until well after midnight. But if you wait a few months, it's going to be well placed high in the south. It's one of my favorite objects. It just has so much lovely structure and contrast in it. I captured this using the same scope, a 10-inch Ritchie-Chrétien, but I used a color camera, a ZWO brand ASI 294, with a multi-narrowband filter to cut through the light pollution. And my final object, the final image rather, we can go to the next picture. Thank you. Is of the moon observing challenge for this month. It is the Archimedes crater. It's the large crater just to the left of center in this image. This picture I actually captured in February of 2018. I haven't had an opportunity to do much solar observing this month. It's an 81-kilometer diameter crater, and it's located on the eastern edge of Mare Imbrium. It has a well-defined rim with terraced inner walls, but the floor has been completely flooded by lava at some point in its history. So it's a nice, smooth, flat bottom. If you look carefully, you can notice there's a difference in brightness and texture of the mountainous region to the south of the crater. You can even see some of the original secondary impacts in the terrain resulting from when Archimedes was formed. So presumably this was some high ground that is sitting above the level of the lava that flooded the floor of the Imbrium basin. It's kind of neat to see the difference in the texture. Another interesting feature is the area around Hadley Rill, and let's see if I can pull up annotation tools. Hey, there we go. So it's not a very good color, sorry, but that is where Hadley Rill is, and this area right here, hopefully you can see the little red cross I'm making. That is the location of the Apollo 15 mission landing. They landed there with their little buggy, and they drove all around that area, exploring the edge of the rill, and the escarpments in the area. So kind of an interesting part of the moon to observe as well. And that's it. Thank you very much.
Hey, Jim, got a question.
Sure.
How far away is that 22 magnitude PGC galaxy?
That I don't know.
Okay.
I don't, sorry.
Somebody will have to far. Okay, that's a good answer. Okay. So thank you, Jim. And we have Gabriel next.
Hi, everyone. So this is, am I unmuted? Okay, good.
Yeah.
So this is my first imaging session with my telescope. So I've only been doing it for a few months. So bear with me if the color correction is not quite on point. I'm still working out a few technical kinks. So this is M51, and we also see the NGC 5194, which is the smaller part of that galaxy, the small right next to M51. And we also have a star, which I annotated. Can you just go to the next slide? All right, so here are the annotation. So we see all of them from the Tycho catalog, and we see obviously M51 and its replacements right beside. So next slide, please. All right, so this is M81 and M82. This was about 9 hours of integration. I'm using a 4-inch Apple refractor. So next slide, please. So these are the annotation for that. We see there's a lot of stuff in that frame. So next slide, please. All right, so this is the lunar challenge for this month. This was done with the NextImage 10 camera. So I do have a bit of color. It's less detailed than Jim's capture because it's only a 4-inch. So we have to live with that. So next slide, please. All right, so this is my first attempt on the elephant trunk. Again, this is about 2 to 3 hours integration, so not a lot of detail, but I think it was a great first attempt on that target. So next slide, please. Again, the annotation. Again, there's a lot of stuff going on there also. Next slide, please. All right, so we have M101 and the NGC 5474. This again was done with a QHY 163M monochrome camera, and I'm using this the Bader 2-inch filter as Jim mentioned. For the luminance one, the 2-inch from Bader, the UV and IR cut works pretty good for deep space and using that in the luminance channel. So next slide, please. Again, so we have the annotation there. So next slide, please. All right, so this is the Iris Nebula. This for the Luminance Challenge, this was actually my first visit to the Fred Lossing Observatory. So I was able to run at a good 2 or 3 hours of just luminance over there. And I've added the data, the color data from what I took from my backyard, which is about Bortle 4.5 to 5. So it's still kind of good, but I found that at the Fred Lossing Observatory, I get like 2 or 3 times more data for the same amount of sub-exposure. So next slide, please. Again, so those are the annotations for that target. So next slide. And I believe that's it. For the annotation, if you want to know, those are made with PixInsight. So once you have your image solved, you can generate all the layover for that. It's very quick and it's very good. It saves a lot of time instead of doing all the manual annotation. So that's all for me, and I might have some better one next month.
Thank you very much, Gabriel. That's great. So next person is JS.
Yes, hello. So like Jim, I captured Leo 1. My just recently kind of started. Oh yeah, sorry, see me. Yeah, so just recently got back into astronomy, kind of like last year, and I bought a Dob and a 10-inch Dobsonian, and found you can't see too much from my backyard, so I decided to throw some technology at the problem. So a few months later, I'm the owner of 2 different astronomy cameras, a Planetary and a one-shot color. So so this one was the first kind of try with my ASI 294. Yeah, so it's a nice target actually. I kind of see it slowly pop out as it stacks. And as Jim was saying, you can see Regulus out of the frame there with the rays coming up. So it's a really nice and challenging target. So next, please. Yeah, so this one here, actually I was playing around with my Planetary camera actually. So it's a very small field of view. That's M51. I mean, the picture has lots of imperfections, but I like the amount of detail that we can see with the dust lanes and the detail in the arms and whatnot. So yeah, I was actually quite happy with that one. Next please. So these are some of the supernovas we can see right now. So I actually got 3 of them. The first one, 2020 JFO in M61. So that one was only actually discovered in the beginning of May. So it actually shows a nice color contrast with there's a line of foreground stars in there, and the supernova is really kind of bluish compared to them. Well, according to the camera and the color correction, anyways. But it's a nice one to observe. And actually, that galaxy, as I was reading up on it, it's actually the 8th supernova discovered in that galaxy since the 20s. So it's quite prodigious for supernovas. Next, please. So this one, yeah. So 2020 FQV. The supernova is a bit dimmer. It's in the Siamese twin galaxies. Another one. Oh, sorry. So just yeah. So what was I saying? Yeah. So there's nice satellite trail going right through it, but didn't go quite slice the galaxy in half. So it's nice, nice little supernova, quite dim. So next, please. This is another one, 2020 HVF in NGC 4568 in Virgo. And that one's very interesting because the supernova totally outshines the galaxy. Galaxy is a very dim little smudge there, but that's not a star. That's actually a supernova in that galaxy. So I was quite impressed at seeing that. So it's about magnitude 20 for the supernova. So the galaxy is even a bit dimmer and quite small in angular size as well. So next, next please. Yeah, so this one's of course M27, the Dumbbell Nebula. You know, the Cygnus and the Milky Way is just starting to come up in the east now, I guess. So it's starting to be visible above my from my backyard, above the trees and whatnot. So it's one of my favorite areas of the sky. So quite a good night with nice seeing and got some nice detail. Just for detail, so all the pictures are taken through my my 10-inch Dobsonian. It's on an Altaz mount, so it's not an equatorial mount. It's just an Altaz mount with stacking. Pictures are about 15 to 20 seconds each, and all the pictures are taken with an ASI 294 color, except the M51, which is with a quite an expensive SV Boni. SV305, I believe it's called. So it's an IMX 290. It's a planetary camera, but I used it for quite a bit of deep sky stuff. Still works. All right, that's it for me. Thanks.
Okay, so we've got Jim Sophia up next.
Thank you. Well, one of my favorite planetary nebulas, N27, was taken with an 8-inch Smith Cassegrain and a Mellencamp Sky Raider DS10C using the Optolong L-Enhanced filter. This is a stack of 5 25-second exposures, and the image was lightly processed with Topaz Studio. Next slide, please. So this is M101, and I took this image off my balcony a couple of weeks ago using Deep Sky Stacker for the first time. With my Altaz mount, field rotation is noticeable as I point closer to the zenith, and M101 was at an altitude of 70 degrees. On a previous occasion, live stacking at 20-second exposures at the 20-second exposure rate continuously resulted in big swirling star trails. So this time I collected 60 frames at 20-second exposure each, and I stacked them with Deep Sky Stacker afterward. I also used an astronomic UHC filter, which works well on galaxies when you're in a light polluted city. So Jim T, thank you for the suggestion to use this program as an alternative for getting a stacked image, especially when conditions call for it. Next slide, please. This is M106, a stack of 8 20-second exposures. And I took this image in the Moose Creek area last year, and I'm hoping to revisit M106 again this year. Thank you.
Thanks, Jim. Next one is Gary Boyle.
Good evening, everyone. It's been a while since I've shown some pictures. This goes back to a moonrise of August 14th of last year. You have to have all your ducks in order to get a moonrise. Of course, no cloud at all on the horizon, so I got pretty lucky on this one. Next slide. On December 1st, I decided to try some stacked images of the Rosette Nebula. I took only a few subs, a couple minutes each, and using an iopton tracker, but I plan to do more stacks this winter. I'm really waiting. I'm not waiting for winter around the corner, that's for sure. Okay, next slide. With the pandemic, we're staying home. My wife and I work from home. What else are you going to do? Help with the gardening, rebuild the good old fire pit, take pictures of the crabapple tree. But then when it gets clear at night, what else are we going to do but image the sky? Next slide, please. So I've set up my my Canon 450D on the iopton tractor borrowed by from Joe Bonner on a huge Meade mount. Believe me, the wind does not move this sucker, that's for sure. The next couple of images will be taken with the 50mm prime lens f1.4, not this one over here, but that's the 24mm. I use my 50mm on the next two. So on to the Milky Way. Next slide, please. So, as I said, 50mm. This is a combination of three minute images on the iopton. I call this 443. It's f4, ISO 400, 3 minutes. I only did 3 of these, but the next night when I wanted to try do more, it got a little cloudy, so I couldn't do any more subs. But I plan to do more over the next few months. And the last slide coming up is. I was very surprised on this one. Next slide, please. There we go. This is the heart of the Milky Way. It's called the Via Lactea, and that was Roman for the road of milk, which we call the Milky Way. The Milky Way consisting of about 300 billion stars. The number fluctuates back and forth. But this is the same 443. 6 images, 6 subs only for a total of 18 minutes, and stacked on Deep Sky Stacker and processed with Elements 10. So very pleased on this, taken from South Mountain, Ontario. I live in the beautiful countryside. So I'll plan to do more of these this summer, but the image just below center is the Lagoon Nebula, and as you come higher from the center is M17, the Swan, and the top pink one there is the Eagle Nebula, which we saw just previous. That's it for me.
Thank you, Gary.
Thank you.
Coming up, we've got Bob Olson. There you go, Bob. You're spotlighted. You're muted, though. Can't hear you, Bob. There we go.
All right, here we go. Am I live now?
You're live.
Thank you. May was a fantastic month for getting out. I managed to get out 12 days in imaging in May alone. Anyway, this is my image that you've seen several times already. This is M61, the supernova, and it's. I took it on the supernova was first noticed on May 8th. And I imaged it on May 13th, 21st, and 23rd. It was still pretty bright on all those days. And it's a type 2. And next slide, please. Whenever you image a supernova, the first thing you do is you go and see if you have an image when it wasn't a supernova. And I found one of my files in 2015 that I took. And there's no supernova, and we'll not play Where's Waldo. Can you show the next slide, please? Yeah, the supernova is right there, missing in the 215 and the 2015 picture. It's a type 2 core collapse of a massive star, and a massive star being 8 to 50 solar masses. Fusion produces energy in any star, where hydrogen turns into helium and so on. And when it reaches iron and nickel, the fusion does not produce any more energy. And so what can happen is the energy being produced by the fusion, it doesn't hold up the star anymore. And when the core reaches about 1.4 solar masses, it collapses. And boy, it collapses hard and fast. It goes screaming into the middle of the star at about 23% the speed of light. And this compression produces temperatures of 100 billion degrees Kelvin. Then it crashes into the neutrons that were produced in the collapse, and it bounces off. It hits and rebounds off, and the shock wave accelerates the rest of the star, the stellar material, to its escape velocity, and the star explodes. During this very brief time element, the higher elements with higher atomic weight than iron and nickel are produced. And so when we say that we are, the products of we are basically supernova stardust, that's what we are. That's really correct. And depending on the original mass of the star, it will form either a neutron star or a black hole when it's finished. Okay, next slide, please. In looking at my files, I noticed back in 2009, I had actually taken another picture of M61. And next slide. That is another supernova from 2008, actually. I took the picture in January. The supernova actually was tailing off at this time. It was in 2008. Okay, next slide. You've seen this several times already. This is UGC 5470. It's a dwarf galaxy, part of our local group. I included the star that it's next to and blasts it out. Anyway, the next slide, please. So that's what we're looking at. That's a dwarf galaxy. It's about 800,000 light years from here. And, I can't even imagine how you'd see this visually, but apparently people do. I can't even guess what. Next slide. And you can see Regulus is almost a magnitude 1 star, and there's this little galaxy sitting there off to the side, still visible even next to Regulus. And next slide, please. Each of those arrows is pointing at another little galaxy. So it's a pretty galaxy-rich area. It might be sort of fun if there wasn't Regulus there. Okay, next slide, please. This is Able 36. I had never heard of it before this. And so whenever I haven't heard of something, I always sort of look it up. And I looked up an image from a guy I know called Adam Block. And his picture was fantastic. And so I decided I'd give it a try. And I forgot that Adam images from Tucson on top of Kitt Peak. And so this is really down in the mud of the southern horizon. And you are looking at 7 hours of exposure to see this. I can't even guess how you'd see it. I think it's like 16th magnitude, and it's a planetary nebula. Absolutely gorgeous. But I never saw it until I started stacking images together. Even my subs didn't have much in them. Okay, next image. M51. This is the very first object that I ever imaged. And so I sort of have a kind of a romantic attachment to it. And over the decades, I have actually imaged this over 70 times. That's not true. I have pointed my camera at it 70 times. It's definitely an old-time favorite. This picture here was taken this May, and it's a combination of 7 nights of imaging. Anyway, thank you very much.
Okay, thank you. So we're going to turn over to Paul Cleninger, and he hasn't changed his name. I'm just, he does not have video, so I'm just going to, that's what he looks like, in case you're wondering.
I thought you were trying to pretend you were me there, Dave.
I wish.
Well, good evening, everybody. I trust you're all doing well out there. As Jim mentioned, we've been fortunate to have some pretty nice, clear nights during May, and so I've got a few images to share with you as well this evening. Last month, I mentioned that we had the possibility of observing a bright comet in our morning sky in mid-May. But like Comet Atlas in the previous month, Comet Swan started to take a dive in its brightness about 2 weeks before becoming accessible to us here in the Northern Hemisphere. You can see here on the chart that the comet reached peak brightness just around the beginning of May, by some accounts attaining a magnitude of about plus 4.7, which would have made it an easily visible object to the naked eye. But there it stalled and started to decline. So by May the 13th, when it started to become possible for us to actually see it here, it had already dropped by at least 1 magnitude. Coupled with the fact that this was at an extremely low elevation for us, observing it visually became a no-go for sure. I was out on several nights, as indicated here, and to see if my camera would fare better than my eyes. So I've got a few views here. Next slide, please, Chris. So this was my first night out trying to capture this little beastie. It was quite clear, but there were low, thin clouds hugging the horizon. And so I had to wait a bit until the comet climbed above those to get a look at it. Next one, please. Yeah, and there it is. Waiting those few extra minutes, though, also meant that the dawn sky was brightening rapidly, making seeing or imaging this thing even more challenging. While the camera caught it with a 200mm lens, I tried seeing it with 15 by 70 binoculars, but I'm not certain that I did. Probably more wishful thinking. Next one, please. So by May the 19th, the comet had climbed a little bit further above the horizon by the beginning of dawn, and so the chances of seeing it should have been better. Unfortunately, it also dropped by about another half magnitude or so, making it even dimmer. This view was taken with just a 50mm lens on a stationary tripod, and you can see that on that night too, there were some patchy thin clouds sailing through. I was initially surprised by the bright streak in the view, but zooming in, saw that it was just a meteor trying to fool me. Next one, please. Yeah, the comet was much more subdued, as you can see here. Having the bright star Algol very close to it, though, certainly made it easier to point my binoculars for a view, but even then, I still am not certain that I saw it. Again, it might have just been a bit of wishful thinking. Next one, please. So this view was really my best night of imaging for this comet. It came about 2 weeks ago on May 21st. The comet again was a bit higher in the sky by the start of dawn, but it also decreased just a little bit further in its brightness. The bright star to the left is Algol, and I took this with a 420mm lens and a Canon 60DA camera. And it's a combined stack of 16 60-second auto-guided exposures. Next one, please. So zooming in for a bit of a closer look, you can see that the comet was displaying very little of the long, impressive gas tail that was prominent to observers in the southern hemisphere only a few weeks prior. It had, however, developed a shorter, broad dust tail seen just to the right of the coma. I did manage to see the comet through my binoculars this night, although just barely. It really wasn't much brighter than the background sky and just looked like a small fuzzy patch. Given the decreasing brightness of Comet Swan, I decided against any further imaging attempts, especially since the month's moonless window was going to be closing soon, and there were certainly other objects of interest in this month that were calling to me. Next one, please. One of those was Comet Pan-STARRS. Pan-STARRS was originally discovered way back in 2017 out near Jupiter, and it's taken a while to reach the inner solar system, but it was projected to reach close to its projected maximum brightness this month, and it was much higher in the sky well before the beginning of dawn than Comet Swan was. So next one, please. You can see that it was also sailing through a pretty interesting region up near the Big Dipper, close to the familiar M81 and M82, as well as the smaller disrupted elliptical galaxy NGC 3077. and also IC 2574, which is a dim dwarf spiral galaxy, also goes by the name of Coddington's Nebula. You can see that down near the bottom. So I'm going to zoom in on that portion of the sky. Next one, please, Chris. Here you get a better view of the comet. And as for Coddington's Nebula, as I said, it is a dim dwarf spiral. And interestingly, it's believed that about 90% of this galaxy's mass actually consists of dark matter. The comet itself, you can see, displays a long, slender gas tail, similar to what Comet Swan coulda, woulda, shoulda been. Anyway, it was nice to have a comet like this up in a much higher portion of the sky to get a much clearer view of it. So the month wasn't all lost for comets. Next one, please, Chris. A little further afield, like you've seen before, with a few of the other folks, I also managed to image supernova 2020 JFO up in M61. This is a magnificent barred spiral galaxy in Virgo, and this image was only taken 13 days ago, and I believe the supernova is actually still visible using a telescope. I'm not entirely certain of that. I haven't heard any updates on it recently, but I believe it's probably still visible. Next one, please, Chris. So I didn't have any previous images of M61 to compare. I searched through my archives, but I guess this is the first time I shot M61. But I did find one that I thought would be an appropriate one to show you. This is one from our old friend Paul Commission, taken coincidentally almost exactly 10 years ago. So I've overlain it here, and note the position of the supernova in my image. And next one there, please, Chris. There's Paul Commission's image of M61 from May the 20th, 2010, and you can see. You can't see the supernova in this. Now you see it. Now you don't. And if you go for the next one there, Chris, now you can see it. So you can see where the blast has occurred. And honestly, it never ceases to amaze me that we can see an exploding star from 53 million light years away. I'm certainly glad that this one didn't pop off anywhere near our solar system. That would have been a bad hair day for sure. Okay, the next one. I also managed to bag the Leo 1 dwarf galaxy. This is really a challenging object for a number of reasons. It's a dwarf spheroidal, and as Jim also mentioned, it's the most distant satellite galaxy to our own Milky Way at about 120,000 light years away. The challenge in observing this object is really twofold. It has a very low surface brightness, making it obviously quite dim. But even worse, it's situated only about a third of the moon's apparent diameter away from the bright star Regulus. So the star's glare can easily swamp this very dim galaxy. If you're just trying to see this galaxy visually, it's usually easiest if you place Regulus just outside the field of view, as you saw in a couple of the previous images. I've included Regulus here just to illustrate how overwhelmingly bright it is in comparison to the galaxy. I mean, Regulus will easily record in a few seconds with most cameras, and this is a stack of 4 600-second exposures taken with an 80mm ED Apo and a CCD camera just to record that very faint galaxy. So an interesting object there, and definitely a challenge. Getting a little late to see that now. Leo is getting pretty low in the west. I'm not even sure if it's still visible up by the end of twilight there, but next time around, when it comes around, certainly worth a peek to see how determined you are. All right, and the last one I have, Chris. This is obviously the Orion Nebula. This is one of the images that was part of the processing segment in the astrophotography workshop that we ran on Zoom on May the 9th. So I just wanted to take this opportunity to thank the folks that made this workshop possible. The workshop was very successful. The Zoom session was amazing. We didn't have really any technical glitches, and we reached quite a lot of folks with that. Mike Mogadam and I started talking about this workshop back last September, and in making this happen, he spent a lot of time organizing the event and answering tons of emails for me. So thank you, Mike. Paul Sadler aided in the project significantly by organizing and running the survey we initially did, and also producing the final videos, which I believe are now available on the RASC Ottawa website for members to download. So if you've got, in this time of COVID, if you've got 5 or 6 hours to spend listening to me yak about astrophotography and you want to try your hand at processing some of these images, those files should be available. I should try to confirm that, and they will be available to all the members, whether you signed up for the initial workshop or not. We've decided to make them available to all members of the club. Mick Wilson also handled all the website work, and thank him for that. I also want to thank Pamela Wolf for getting us the classroom back at Carleton University back in March when we tried to run this initially. You remember those times before the COVID era? Yeah, we only were able to run the first session, and when it came time for the second session, it was already a no-fly here in Ottawa. So as a result, the reason I mentioned that the videos are 5 hours long is that I did a recap in the first segment of that session back in March. So it's basically almost a full recap of that first session. And then the second session, which runs for the 3 hours, is concentrated on the image processing side of things, and has 3 exercises ranging in levels of complexity. And the last one was this one here, the Orion Nebula. So it was an interesting exercise if you want to try your hand at it, and using the freely available and very capable GIMP image processing program. And last but not least, Chris, I want to thank you for driving the Zoom Starship. You've made all of this, not just in our workshop, but in our meetings, much more easy. And I'm glad that we have this outlet to still reach out to one another and share the things that we're doing. Thank you, everybody. Stay safe.
Thanks, Paul. Okay, so we're on to Taras. You're spotlighted. You need to unmute yourself. There you go.
Just did. Hi. Hello, this is my rendition of the Swan Comet. It was indeed a really difficult object, as Paul described. Paul gave a great analysis of behind the comet's appearance in our northern hemisphere, and unfortunately it was really difficult to see it because it was too low above the horizon, but also the comet itself was really dimming quite fast. So this image was taken on May 20th. This was early hours, about maybe 3:40 a.m. As you see, the sun was close to the rise, and when looking for the comet, it was twice as disappointing because of this thick layer of clouds along the horizon, which I did not see until the comet was much higher. The comet was higher, the sunrise was closer, so the background is still quite bright, but I'm proud, like you can see the on the left from the comet, the bright star of the bright star called Algol, if I'm not mistaken. So I'm happy that it showed up at least as a recognizable smudgy dot, and it was quite an experience. Next slide, please. So this was taken on May 23rd, a few days after that, from a place with a wide open west horizon and, east horizon in this case. No, sorry, my bad, west. This is the sunset, and you can see a very, very thin slice of moon. This is the moon of, again, May 23rd, which had a special significance for Muslims. It was the beginning of the holiday Eid Mubarak. So what also is interesting is that above the moon in the upper right corner of the picture is Venus. The higher resolution version of this picture shows the Venus as a very thin crescent. And even more to that, if I had a lens which had a bit wider angle, then above Venus, maybe same distance or half of a distance between Venus and Sun, but up, there was Mercury as well. So this is quite rare event when Mercury is higher than Venus, but it was, if you go to the next slide, please. Oh, okay, yeah, so before we go to Mercury, this is the Venus, what it looked like back then. You can see it's very, very narrow crescent, quite large in size actually. This was 55 arc seconds in the diameter in the sky, and it's from the same time when the previous picture was taken, so it's on a blue background of evening sky. It was very close to the sun. It's getting even closer now. Around this time, I think it's around more or less the location where the sun is itself. So we will not see Venus until late June when it starts reappearing during the sunrise hours. And I also took a video. This is a visual range pictures, no filters because planet was quite big. I stacked this and you can clearly see the nice tiny crescent of this planet. Let's go, next slide, please. So Mercury was just above the Venus, and it's a rare beast. It's difficult to catch it because it's close to the sun and it circulates quite fast. But because it's an inner, with regard to us, a planet, which is between, the orbit is between us and the sun, so it has the phases, same like as a moon. So this picture was taken on May 20th or 23rd, if I'm not mistaken, when the phase was half illuminated, I would say, waning phase. And I'm happy that this actually showed up like this because, again, the latitude, the elevation was quite low, and the challenge is there to catch that, especially as you can see it also on a quite a bright background. Let's go to the next slide. So with the span of next few days, I was trying to get a better picture of Mercury because it was every few days it would be a little bit higher above the sun. So you can see the progress, how the image improves because the planet is higher, a little bit higher. It wasn't too high, it was about maybe 15 degrees, but still with the help of filter which corrects for the dispersion, I managed to correct that rainbow-like appearance of the planet. And you can see a bit of a change in the size as well, from 8.4 arc seconds on May 23rd to around 8 arc seconds on June 1st. Let's go to the next slide. Mars, so this is 8.7 arc seconds diameter, right? Actually, this is not right now, this is May 21st. And it was visible, it is visible now on the southeast. It's still quite small, but what I like about this picture is that you can see the polar cap on the top and a little bit of some details on the surface of the planet. It's still quite small and barely distinguishable. But that night when I took this and other planets was really excellent seeing, which rarely happens. So I, of course, didn't miss a chance to take some other pictures. Let's go to the next slide, please. And Saturn, also the same night, May 21st. This was about 41 arc second size. With if you add the dimensions of the rings as well, you can see a bit of its moon on the top. And I didn't expect this because it's still quite low. This year is actually not too good for planets. Both Saturn and Jupiter will not be rising higher than 22 degrees from our latitude. So I was quite happy that night. Again, was great seeing, and it did show the details, a little bit of the surface details and the double nature of the rings. Let's go to the next slide, please. And Jupiter, so this was again 22-degree elevation. This diameter is about 46 arc seconds. This picture was taken earlier on May 13th, when the seeing was not that good, but it still showed up a little bit of details in the bands. Let's go to the next slide, please. And the same night on May 21st, however, with a great seeing, there were quite a few events happening with Jupiter. First, you can see there is a Ganymede, if I'm not mistaken, passing between us and the planet and casting a shadow on the surface of the planet. There are other moons, one on the left and two others on the right. And I was taking that in the span of like every 5 minutes to see the dynamic while it was still actually possible, because this was early morning hours. And when processing these pictures, the last at the bottom, I noticed that there is something strange. One moon is missing. So as you see, the next to the right next to the planet, the moon is not there. I thought it may be something to do with maybe the noise level, or maybe there was like some smudge on a sensor, but no, it showed up clearly that the moon is just not there. Apparently, it's quite an interesting event. This is when the moon gets into the Jupiter's shadow. So you can see a bit of a shading in how the planet is lit. The sun comes from the right, and when it illuminates the planet, the shadow, sorry, my bad, the sunlight comes from the left, so the shadow is on the right, and this is where the moon was. So let's go to the next slide, please. This is, I took a look at that situation later with Stellarium, and it showed clearly the same location of the same moons with regard to the planet. And if you could play it, please, Chris. You can see how Io advances into the shadow and all of a sudden disappears, and that's what happens. So the moment when the moon gets into the shadow of the planet, it has really significance, because all of a sudden the moon is just not there. And it's significant to the extent that it was noticed by Danish astronomer Romer, who was observing the moons of Jupiter, and he found out that the period during which Io rotates around the planet is 42 hours, 29 minutes, and 3 seconds. But he also noticed that some periods of the year, there is a difference in this Io's rotation period, up to 30 seconds. So he didn't have an explanation, and he actually showed his research and the results to this Astronomical Society. And if I'm not mistaken, Huygens came with an explanation that this is because there is a limitation to the speed of light. So when Earth moves towards Jupiter, the distance between our planet and Jupiter is much smaller. So these disappearances, the fact of that disappearance, the moment when the moon hits the shadow, it takes much shorter than when the Earth is on the opposite side, coming away from Jupiter. And this difference is as significant as 30 seconds. So I'm happy that I managed to catch that fact, which was quite unexpected, because all of a sudden, as you saw, the moon just disappeared from the view. Thank you. That's it.
Okay, thank you, Taras. So John Thompson, you are up next.
Just unmuting.
Your audio's not very clear there, John.
Okay, I thought I might be the only one who had captured the conjunction between Venus and Mercury, but I see Terrasse had done it also. This was done on the night of May 22nd when the closest approach between the two planets happened. I also have another shot of the previous evening, May 21st, which was also the night of the new moon, where Mercury was below Venus, about the same distance, but a bit further in about a 7 o'clock position. But these were fairly low in the west. You needed a fairly good west horizon in order to see these. Next shot. Next slide. I also wanted to see if I could get a photograph or an observation of Comet Swan. So what I first did was I set up using Stellarium on the night of the 21st, and you can see my up in the right-hand corner the settings. I was using a Canon XT and a 135 millimeter f2.5 telephoto. That's a nice combination. That's one of my favorite lenses. And I found, you can see that reddish rectangle, that if I put Algol in the upper right-hand corner, I could get not only Swan, but also the remnants of the Atlas. Like both of those were supposed to have been comets that should have been giving nice performances, but both of them fizzled out as it happened. And I didn't know if it was possible, but Stellarium was telling me that Atlas was magnitude 5.8, which made me wonder if it was perhaps possible to get those fragments. But I wanted to wait until the comet Swan at least was above 10 degrees. This setting scenario shows them at 3:55 a.m. and it's about 9.5 degrees. So I thought I'd be a little bit after 4 a.m. when I actually shot it, but I got there early just in case to set up. Oh, and normally I shoot these off my back deck, but in this case, neighbor 2 lots over, some trees that were getting in the way. So I had to move to a side road about a mile away from my home. Okay, next image. So this picture I set up at 3:55 a.m., which is about the same as what that previous Stellarium shot was. And you can see that even then, the twilight was coming in. The sky to my eyes was darker than that, but I had to boost the brightness in order to see the comet at all. And you can see Algol is up in the right-hand corner there. And then to the left is just barely see it as Comet Swan. And one thing I noticed that its position isn't exactly the same as what Stellarium predicted. The Stellarium showed it a little bit to the left of where it actually is, that it made an angle of that line of 3 stars above it. It made an angle of slightly more than 90 degrees, and here you can see it's less than 90 degrees, which means either that Stellarium's orbital elements were a bit out of date, or possibly there's what were known as non-gravitational effects were happening. That's not unusual for comets, as the outgassing of the tail can form a jet reaction effect and make the orbit slightly different than what it would be if it was purely under the motion of the sun's gravity. And then off to the left, there's where the fragments of Atlas T4 would have been. That even if that tree hadn't been there, I'm sure it was too low. Like at that point, they're only about 3 or 4 degrees above the horizon. And by the time I had actually planned to get these shots at between 4 and 4:10, by that time the sky was brightening so much that it was impossible to get it. In fact, by 4:10 or even 4:05, Algol wasn't even possible to see it. So there you go. There's 2 fizzled comets. Well, there's actually like a set of fragments of comets of Atlas over to the left. And then I did zoom in to get a slightly better image of, next slide, please. And there in the middle is Comet Swan. You can see that it does have a slight tail, like a comet image. Compared to those stars in there, I estimated it at around 8th magnitude. Other people were estimating it at about 7.5, but again, like Paul, I couldn't see anything there with binoculars. It was virtually impossible because the sky was getting bright. And even 5 minutes later, it was impossible even to find Algol to set up. The next one. And finally, this was one that, that everybody else was imaging, and I decided to image it too. That's M61. And again, you can see the supernova. Several of the images, including mine, you see some knots in that arm to the left, which I believe are H2 regions. This galaxy is actually an extremely active one compared to our own galaxy. It's about 55 million light years away. It's roughly the same size and mass of our own galaxy. But unlike our own, it's very active. It's called starburst. Our galaxy has had 8 observed supernova in the past 2,000 years, which is an average of 1 every 250 years. This one has seen 8 supernovae since, I think it's 1926, about 100 years. So you can see it's a much more active. This is the 8th supernova. And then the next one, I just annotated it to show where the supernova was. Oh, next slide, please. Just pointing out the supernova. I saw somebody else's image. It was taken 4 nights before this one, and his image showed the supernova was about the same brightness as the star below it. So you can see it's dimmed slightly, but this one was taken on the night of May 23rd, and I think that's the night that a lot of people were doing it. This is a total of about 18 minutes of exposure. There was something like 25 or sub-exposures, and I was using a Canon DSLR. The image was very small on the fairly large chip, like a 23 millimeter chip. So in this case, I had to crop it and then blow it up by a factor of about 4. And you can see also that there are at least 4 other faint galaxies in the field, like 2 above it and then 1 directly to the right beside that bright star. And the refractor I was using is not a fully color corrected, like it's not an apple. And as Jim was saying, that does mean it's a little bit of chromatic aberration. You can see a bit of a blue tinge there, and a fringe killer would have killed that. The one thing I might mention to Jim, that I have a really old broadband light pollution filter, which was made in the days where low pressure sodium is the most common light fixture. So there's a notch in the yellow, but those things actually do very well at both fringe killing and producing nice contrast on planets, because they also cut out the blue and violet end of it, which is where the mercury vapor lights have a lot of their emission. So using one of those broadband light pollution filters sort of does a double duty. It increases the contrast and acts as a fringe killer too. A few other people I know, I've read about it, noted that fact. So I guess that's it. That's the last image I have. So I guess over to Chris.
Thank you, John. Okay, so I'm going to turn it over to Chris and spotlight your video. There you go.
Great. Thank you, Dave. I think if people recall 2 months ago, we heard from Paul. We had all been excited about the great comet that was going to be naked eye during the sky, and Paul explained how it wouldn't happen or how it fizzled. So last month he got us excited by Comet Swan and promised that it was going to be spectacular and naked eye, though low in the sky. So with that promise, I was very pleased when Paul invited me to come out with him for 2 nights along with Taras to attempt to image it. And he's explained to you the difficulties we had, the compromise between waiting longer for the comet to rise in the sky, but the sun being there. But someone like myself that doesn't have the vast experience of Taras and Paul, just simple exposures, I was actually pleased to capture the comet. There's another version again with a plane flying through it. So even though it was a disappointment, I really enjoyed the process of going out and struggling to find it and trying our best to capture it with some success. Same time, building on the theme that others have talked about, particularly being up at our cottage recently, there's been some spectacular sunsets over the last month, and lots of fellow cottagers showing images. And they coincided with this conjunction of Mercury and Venus. So the next image I have here was actually particularly pleased with, because I managed to capture 5 planets in the sky, 5 planets at the same time, even though there were only 2 in the sky, and there was nothing wrong with my optics. So as you see above the trees, I managed to get Venus and 2 more versions of it reflecting in the lake, as well as Mercury and another version of it down in the lake. So 5 planets in one shot. And then a close-up of Mercury and Venus as they were setting over the trees. My horizon is 5 degrees, so I didn't get very long to capture images of those. And that's it.
Sorry, I had myself muted there. Okay, so let's take a look. We have some challenges, thanks to Oscar here. So last month, our beginner challenge was M51, intermediate challenge was April 36, UGC 5470 was the advanced, and the lunar challenge was the Crater and Montes Archimedes. And I'm glad to see that we did get some images of these, so that's super. Next slide. So our deep sky challenge this month is Messier 64. It's a black eye galaxy. It's around 8th magnitude, and this will be the beginner challenge for this month. Next one. Intermediate challenge is NGC 5529. It's a spiral galaxy in Boots. It's 11th magnitude. And our advanced challenge is the Planetary Nebula in Sagittarius, NGC 6578. It's 13.5 magnitude. And then our lunar challenge is an ancient lunar impact crater, Crater Katharina. It's located near Rupi's Altai. It's 100 kilometers wide and 3.1 kilometers deep. And here's a summary of these challenges. These will be posted on our website, and you can also take a look at these when the video gets posted from tonight's meeting. Next slide. Okay, so our members only Fred Lawson Observatory is open, but the buildings are closed. And currently in Ontario, we're not supposed to gather with more than 5 people. So maybe exchange some emails just to make sure we're not getting too big a crowd out there. And of course, we should always respect the physical distancing rules while we're out there. Well, Estelle doesn't have a pick because the library is closed and because it's located within the museum. Hopefully at some point we'll get back to that. Here are the people that look after your club, and thanks for all the work that they do. We have, I think we got up to about 106 people, peaked at that, 107 people tonight. Thank you to everybody, the organizers and speakers for tonight. And thank you to the RAC National Office, who's loading us their Zoom account to allow us to do these meetings. Unfortunately, our post-meeting entertainment is not available right now, so have a beer at home. If you're interested in becoming a member of the Royal Astronomical Society, regular membership is $88. Family membership is $82.50 plus $15 an adult and $8.10 a youth. And youth memberships are $53. Now, at this point in time, if you're having financial challenges, as many people are with all this COVID stuff going on, and you need some assistance with your membership, please don't hesitate to contact our local president here, president@ottawa.rasc.ca, and we'll see what we can do to assist you with your membership costs. Other membership benefits is that we have the Ted Bean Telescope Library that you can borrow telescopes from. We have our private observatory located on the Mill of Kintail out near Almont. And once our library reopens, you'll have an opportunity to borrow books from there. Additionally, as a member, you do get Sky News every 2 months. You get the Journal every month, the Observer's Handbook once a year, and we have our amazing locally produced Astronauts, and that goes out electronically. Okay, so our next meeting is Friday, July the 3rd, and it will be again on Zoom. And Jeremy Kazoob, you remember when he did his whole thing on auroras? It was quite fascinating. He's going to be focusing on how to photograph the auroras. So that's the plan for our July meeting. And the other thing I'm looking for the July meeting, in addition to observations, is I would like to have folks share some of their favorite gadgets or favorite modifications that they've done to their equipment to share with others. So if you've got some ideas, please send me an email to meetingshare@ottawa.rasc.ca. And so we'll have like a gadget or a handyman corner or something like that. I've got to figure out how I'm going to pull all that together. And so that is July the 3rd. And on August the 7th, we have Paul Cleninger doing astrophotography. And I've just confirmed today that we are having Dr. Christian Sass, who is in charge of the iTelescope network. He's going to talk to us at our September 11th meeting. So any ideas for meetings or speakers, please send them to me. I'd be happy to slot you in. So thank you for coming out tonight. And are there any more slides, Chris?
That's it, Dave. And you managed to pull this off virtually dead on in schedule. Congratulations.
Okay, thank you. So thanks, folks. We'll see you next month. Stay safe. And we'll see you on July the 3rd. Have a good night.